The standard model of particle physics is extremely successful in explaining the behavior of subatomic particles, but it leaves some big questions unanswered. Perhaps the most important one is, where does mass come from in the first place? And why are there different generations of both light and heavy particles with very different masses? The proposal from the 1960s by Peter Higgs was a mechanism where mass is ascribed to all fundamental particles. And the search for the Higgs particle consumed high-energy physicists for over a decade. So scientists were building this schema to make sense or find patterns in the arrangement of subatomic particles, but it still didn't make complete sense. The zoo of subatomic particles seemed unnecessarily cumbersome, and the standard model of particle physics had 24 or maybe 26 different parameters, which didn't make it seem very elegant or simple at all. In particular, there was nothing in this scheme that suggested where mass came from in the first place, or why there were different mass ranges for these three generations of particles. In the 1960s, a theory was proposed called the Higgs mechanism, whereby another particle, the Higgs particle, was responsible for generating the mass of all the particles in the universe and in nature. This mechanism remained a hypothesis for several decades. It was with great excitement in 2011 and 2012, and then 2013, the Large Hadron Collider at CERN started to produce evidence of the Higgs particle itself, the mechanism by which mass comes to all matter and, of course, everything in the universe. The Higgs particle is a little hard to understand.
If you've been paying attention to the news lately, you've probably heard a lot about this Higgs boson, or the God particle. But what exactly is Higgs boson? Well, you probably know that all matter is made up of atoms, and all atoms consist of nucleolyses, protags, and electrons. So what keeps them from bouncing all over the place? Higgs boson. Brendan Higgs was a Dutch sheep herder who had a weakness for drug-induced hallucinations. During one of his more severe acid trips, he thought he saw a large bison chasing and devouring his sheep. It was then that he had a eureka moment. He compared this imaginary bison to a then unproven particle that kept the nucleolyses, protons, and electrons in check. And until very recently, Higgs boson was merely a theory. But the magical tubes in a laboratory called CERN proved this theory when they smashed rocks together so hard that the resulting sparks resembled the shape of a bison, thus proving the theory. So why do so many people refer to Higgs boson as the God particle? Well, that's easy. When scientists first heard of the theory, they all shouted in unison, "God!" Why didn't I think of that? So there you have it, the true story behind Higgs biscuit. Don't trust the media or Wikipedia or your stupid science teacher. Trust me, a guy who makes YouTube videos.
Jack's Films.
A detailed physical explanation of the Higgs requires high-level mathematics of field theory, but we can use an analogy to try and understand it. To a physicist, the Higgs particle is really a field, something that permeates all space, giving the attribute of mass to particles. We can imagine it as a field that's viscous, and so as a particle moves through the space and through this field, the resistance or friction or inertia in this field gives mass to a particle. The more resistance or friction or viscosity, the higher the mass of the particle. In other words, mass is not a fundamental attribute of matter or nature, but it's an attribute applied by the presence of a field that exists throughout space.
Ever since the accelerator turned on, like a year ago, it's been really totally crazy here. Because everybody comes and sends their students, and it's the center of the world for particle physics. Things have been running really smoothly. The accelerator is working really well, it's going really fast, we're getting a lot of data. So everybody's really excited. We can discover something any moment. You can hear about some amazing discovery. We're always looking at the data wondering like what's going to pop out of it. Who knows what, right? This is when, last time we talked about surprises, this is when the surprises might happen. So any day could be the day that changed the world. The LHC it's really all about discovery and exploration. We're looking for different kinds of things, new crazy kinds of things. I mean, to make up everyday matter, you only need the electron, the up quark, and the down quark. Because with the up quark and the down quark, you can make a proton, or you can make a neutron, right? Electrons and protons and neutrons, you can make any atom. So you only need these three. But there's, how many particles are there we've discovered? 12? Why do we have them? I don't know. How many are there? 100? A million? Only 12? We don't know. We're like looking at the tip of the iceberg here and wondering, is there a huge iceberg under the water, or is this it? And what does it mean in either way, right? We're looking for patterns. It's just like the periodic table. You take all the elements and you organize them by their characteristics, and they fall into categories. And these guys over here tend to behave one way, these guys tend to behave another way. Why? Because there's a fundamental underlying structure. And now we know it's just electron orbitals around nuclei. So we have a periodic table of the fundamental particles, and like the periodic table, we've been putting it together and trying to organize it by the characteristics of the particles. And it has some interesting features. It has patterns which suggest there must be some sort of underlying structure that we don't understand, but we haven't seen it yet. There's 6 quarks. Up, down, charm, strange, top, bottom. These guys we call leptons. These are just names. There's electron, muon, tau. And these guys interact with each other. These two interact with each other. These two interact with each other. Same way, these guys are paired. There's all these pairings. Is there more here? We don't know. What's the source of the patterns that we see in this table? We don't know. They're trying to figure out clues by figuring out what other kind of particles also exist. Like, what is out there? The thing is, we have this collider. And the magic of a collider is you can make kinds of matter in a collider that you don't have around. You can take 2 kinds of particles and annihilate them. And it's not like what comes out has to be a rearrangement of what went in. It's this quantum magic where it sort of disappears into pure energy, and then you can make any sort of particle for which you have enough energy. It's like you have a menu. You go to the restaurant, you have a menu, you're like, I have this much energy, so I can make anything that costs that much energy or less. So that's why you want to have as much energy as possible. And every time you crank up the energy, you could be exploring a whole new energy range, a whole new regime. It's like landing on a new planet, stock full of new particles nobody has ever seen, because nobody ever had the energy to make them. And as soon as we get over the threshold, boom, they just pop out. And so one of the things people predict is the Higgs boson. The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? Mm-hmm. Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons. Some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when 2 things both have mass, they attract each other. Interestingly, you can't have negative mass or repulsive gravity. So gravity is different from other forces that way. The Higgs theory starts with this. Imagine a field that permeates the entire universe. And every particle feels this field, is affected by this field in different amounts. So some particles are really slowed down by interaction with this field, like swimming through molasses, and other particles hardly feel it. So the ones that hardly feel it, they have a small mass. The ones that are really affected by it, they couple strongly to this field, are slowed down a lot, they have a large mass. So you've turned the question of why do particles have different masses into a different question. Why do particles feel the Higgs field differently? But there is one manifestation of the field is the existence of this particle. So there's lots of different reactions that could give you the Higgs. For example, one is you could have 2 gluons that fuse, give you a Higgs boson, and the Higgs could decay into 2 bottom quarks. The problem is there's lots of other ways to make 2 bottom quarks. In fact, it's one of the most common things to make. You expect that to happen a million times more often from other kinds of processes than from the Higgs. The thing is, we can't see these reactions. We can't watch them and slow them down, reverse them. All we can do is see the reaction, the decay products from the reaction. So this part is all you see, and what you really want to know is, did this intermediate state exist? Alright, so the collision happens, it lasts for like 10 to the negative 23 seconds, and you get 1 measurement, right? So if you say, well, I'm going to plot the mass, the total energy of this guy. I'm going to add this guy and this guy together and add the total energy. This is this axis here is number of collisions. You do an individual experiment, you get 1 measurement, right? Here. You do another one, you get another measurement. You do another one. Eventually you build up your data, right? And the data looks like this, for example. And then you have 2 theories, right, that predict the data. One says, well, I'm going to predict there's no Higgs boson, so the data should fall along this line. And the other is I'm going to predict that plus a Higgs boson. And the problem is The difference between these two theories is very small. And so it's very hard to distinguish these two with our data because the predicted effect is tiny, right? If the predicted effect were huge, it'd be very easy to tell the difference between with Higgs boson or not with Higgs boson. But the predicted effect is tiny, and so it's really hard to see. What you need is a huge amount of data. You need to take a bajillion collisions before you can see the difference. That's why we run this thing 40 million times a second, all day, all year, to get a lot of collisions to tell small differences between theories. It's like when you take a picture of the sky. You just take a picture, you get a little bit of light. The longer you leave your telescope looking at the sky, the more you can see farther away things. But there's lots of other things that make the Higgs. There's 10 other ways you can see the Higgs. There are people working on that one also. We work in a collaboration of thousands of people, and there's people working on every single channel. Some people are working on this one, some people are working on this one. And the idea is to try to look everywhere simultaneously to see a little bit of evidence here and a little bit of evidence there and a little bit of evidence here can be combined into convincing evidence. So we're going to leave it running for a long time and hope that something new pops out. There's still a possibility for a lot of new things. We've been running for a little while. We haven't seen anything crazy yet, but there could still be crazy pink elephants in there waiting to pop out. That's why I was saying earlier in lunch, like any day somebody could say, oh, we see something exciting. Every time you open your email, like that could be the time you heard about, or every time your student makes a plot, like, what's in the data? What's in the data? It's exciting.
The discovery of the Higgs was an electrifying moment in physics. Will lead to a Nobel Prize. After 2 seasons of data, the Higgs was detected at an energy of about 125 billion electron volts, within the range of the Large Hadron Collider, and was detected at a level of significance equal to 5 standard deviations, which is the gold standard in most science experiments. The detection was validated, and it fit the parameters of the theory. But not everything remains understood, because having detected the Higgs at this particular mass or energy range, other phenomena were expected that haven't yet been seen. The atomic nucleus has not yielded all its mysteries.